Our universe should have annihilated itself into pure light. Every particle of matter created in the Big Bang had an antimatter twin, an opposite and perfect mirror, destined for mutual destruction. Yet here we are, a cosmos filled with galaxies, stars, and planets. This video will give you the complete story of why the laws of physics favor matter, revealing the monumental hunt for answers that defines modern science. How did a 1 in a billion surplus of matter survive to build everything we see, and what hidden forces wrote that bias into reality? What does it feel like to know your existence hinges on a cosmic coin toss that somehow landed in our favor? That perfect mirror is the heart of the mystery. For every particle that makes up our world, there exists an antimatter twin, a doppelganger with the same mass but the opposite electric charge. Take the humble electron, a tiny, negatively charged particle that orbits the nucleus of every atom. Its antimatter counterpart is called a positron, identical in every way except it carries a positive charge. The same rule holds true for the building blocks of atomic nuclei. A proton, which is positively charged, is mirrored by a negatively charged antiproton. Even the quarks that make up protons and neutrons have their own antiquark reflections. This symmetry is breathtakingly elegant. Our most fundamental theories of physics are built on the idea that the universe does not play favorites between matter and antimatter. They are two sides of the same cosmic coin, created in equal amounts, destined to meet and vanish in a flash of pure energy. When an electron meets a positron, they annihilate. When a proton meets an antiproton, they annihilate. This process is 100% efficient, leaving behind only light. According to this perfect ledger, every particle created in the Big Bang should have found its opposite, resulting in a universe that was stillborn, a brief, brilliant flash of radiation that faded into an eternal, featureless dark. But the ledger is not balanced. The very fact that you are here to ponder this question is proof of that. We live in a universe of something, a cosmos sculpted from stars and planets, all made of matter. This means that in the earliest moments, for every 1 billion antimatter particles, there were 1 billion and 1 matter particles. That 1 in a billion surplus is all that remains after the great annihilation, the ashes from which every galaxy was forged. This is the foundational paradox of our existence, a single, unanswered question written into the fabric of everything we see. How did the perfect mirror crack? That 1 in a billion surplus is the only reason anything exists at all. To understand how this happened, we need to step back into the universe's first moments, a time of unimaginable energy and chaos. In the searing heat of the newborn cosmos, energy was condensing directly into particles, but it did so in perfectly matched pairs. For every quark, the fundamental piece of matter that builds protons and neutrons, an antiquark was created alongside it. This was a universe of perfect, furious symmetry. If the story had ended there, those pairs would have found each other almost instantly, colliding and vanishing back into the light from which they came. The result would have been a cold, dark, and utterly empty expanse, a cosmic void with no structure, no stars, and certainly no observers. The fact that we are here having this conversation is the ultimate proof that the story did not end there. Something broke the symmetry, something tipped the scales ever so slightly in favor of matter. Physicists call this pivotal event baryogenesis, the genesis of baryons, which is just a technical term for the heavy particles like protons and neutrons that make up atomic nuclei. This process had to accomplish one critical task. It had to create from that initial state of perfect balance, a tiny, persistent imbalance. Think of it like a vast, cosmic coin-tossing contest where every flip should produce exactly 1 heads and 1 tails. But in those first fractions of a second, the rules of the game were subtly rigged. For every 1 billion pairs of heads and tails that cancelled each other out, the universe produced one single unpaired heads. That single surviving heads is our entire material reality. After the Great Annihilation concluded, when all the matter and antimatter pairs had finished destroying each other, that one extra quark in a billion was left behind. From that infinitesimal surplus, every galaxy, every star, every planet, and every atom in your body was eventually built. The hunt for the cause of this asymmetry is not just a niche puzzle. It is a forensic investigation into the very laws that govern existence. Why did the universe favor matter over antimatter? What hidden clause in the contract of reality allowed this imbalance to form? Finding that clause requires us to look for cracks in what we thought were perfect mirrors. This profound question found its first scientific answer in the mind of a man who understood the weight of opposing forces. In 1967, the Soviet physicist Andrei Sakharov, a figure who would later become a Nobel Peace Prize laureate for his human rights advocacy, turned his formidable intellect to the cosmos. He laid out a precise and elegant blueprint, 3 conditions that any successful theory of our existence must satisfy. He transformed a cosmic mystery into a solvable physics problem, giving researchers a checklist for reality itself. The first condition seems almost obvious in hindsight. The early universe had to be out of thermal equilibrium. Think of a perfectly mixed steaming cup of coffee left on a counter. It is in equilibrium, a uniform temperature throughout, with no energy flowing from one part to another. In such a calm, balanced state, nothing new or interesting can emerge, no structure can form. But the Big Bang was the opposite of calm. It was a state of violent, rapid expansion and cooling, a frantic rush away from that perfect, hot uniformity. This chaotic departure from equilibrium was the essential stage, the turbulent environment where the ordinary rules could be temporarily suspended, allowing something extraordinary to happen. Sakharov's second condition gets to the heart of the matter, literally. There must be processes that violate the conservation of baryon number. A baryon is simply a heavy particle like a proton or neutron, the stuff of atomic nuclei. Conservation means the total amount of something never changes. It is a fundamental accounting rule of physics. For a very long time, physicists believed the total number of baryons in the universe was a fixed, sacred constant. But if that were true, our surplus of matter could never have been created from an initial state of zero. Sakharov declared that, in those first moments, the ledger had to be breakable. The total amount of matter in the universe had to be able to change, to increase from nothing. Some new, powerful interaction had to tip the scales, writing a permanent credit into the cosmic balance sheet where before there was only a perfect zero. The third and most subtle condition is where the true magic lies. These matter-creating processes must violate not one, but 2 fundamental symmetries of nature. They must break charge symmetry, known as C-symmetry, and they must break the combined symmetry of charge and parity, called CP symmetry. Let's unpack what that means without the jargon. Charge symmetry suggests the laws of physics should work identically if you swapped every particle with its antiparticle, turning the universe into a mirror made of antimatter. Parity symmetry suggests the laws should be the same if you viewed the universe in a mirror, flipping left for right. For decades, physicists believed nature respected these symmetries absolutely, that the universe was fundamentally impartial and unbiased. Sakharov's brilliant insight was that this perfect impartiality is precisely what would have doomed us to non-existence. If the forces that created particles treated matter and antimatter with perfect, equal-handed fairness, they would have created them in exactly equal numbers, leading to total annihilation. For a surplus of matter to emerge, the laws themselves had to contain a hidden bias, a tiny preference for producing matter over antimatter in certain rare interactions. This bias is what we now call CP violation, a faint crack in the mirror of reality. It is the mechanism that could have made that crucial 1 in a billion difference. Sakharov provided the recipe, but the hunt was now on to find a real physical process in the universe that could act as the chef, one that could meet all 3 of his demanding conditions and finally explain our being here. That hidden bias Sakharov predicted was not just theoretical, it was a crack waiting to be found in the very fabric of reality. The first tangible evidence came from a force so fundamental it governs the decay of atomic nuclei, the weak nuclear force. For a long time, physicists held a deep-seated belief in a kind of cosmic fairness, a principle known as charge symmetry. It stated that if you could magically replace every particle in an experiment with its antiparticle, flipping all their charges, the outcome should be exactly the same. The universe, they thought, was impartial, a perfect mirror between matter and antimatter. But in the 1950s, a series of delicate experiments began to reveal that this mirror was flawed. Researchers studying a form of radioactive decay watched as certain particles emerged spinning in a specific direction, like tiny, whirling tops. When they created the antimatter versions of these particles, the antineutrinos, they did not simply mirror the behavior. They spun the opposite way every single time. This was not a random fluctuation, it was a law written into the interaction itself. The weak force, it turned out, had a handedness, a preference. It treated the left-handed neutrino and the right-handed antineutrino as fundamentally distinct entities, not perfect mirror images. This was the violation of symmetry, the first concrete proof that nature itself could tell the difference between matter and antimatter in certain processes. The perfect mirror had a crack, and through it, scientists caught their first glimpse of a universe capable of bias. This discovery was electrifying, a direct validation of one part of Sakharov's vision. Yet, for all its importance, this single broken symmetry was not enough to save the universe. The effect was too small, too specific. It showed that the mirror could be broken, but the crack it revealed was not the one that wrote our existence into being. The hunt had to go deeper to find a violation that was stronger, more profound, one that could truly tip the cosmic scales. The search for that deeper crack in reality led to an experiment of almost impossible precision. In 1964, physicists James Cronin and Fitch designed a study to probe one of the most ephemeral particles known, the neutral kaon. This particle is a quantum chameleon, constantly oscillating between being matter and antimatter, a living embodiment of the symmetry physicists were trying to test. According to the perfect mirror principle, this particle and its antimatter twin should decay in exactly the same way, producing mirror image sets of other particles as they vanished. Cronin and Fitch built an exquisitely sensitive detector to catch these decays, expecting to see that perfect reflection. What they found after painstaking analysis sent a shockwave through the foundations of physics. The decays were not perfect mirrors. In a tiny but definitive fraction of cases, about 0.2% of the time, the matter version and the antimatter version of the kaon decayed into different end products. This was not just a violation of charge symmetry, it was the violation of CP symmetry, the combined mirror that Sakharov had declared essential. The universe, on this fundamental level, could tell left from right and matter from antimatter simultaneously. It had a preferred direction, a built-in bias. The impact of this discovery cannot be overstated. That 0.2% asymmetry was the first direct, irrefutable evidence that the laws of physics themselves are not perfectly impartial. The cosmic coin was subtly weighted. For their work, Cronin and Fitch received the Nobel Prize, and the physics community finally had its smoking gun, a concrete phenomenon that met one of Sakharov's most critical conditions. Yet, this triumphant discovery immediately presented a new and deeper puzzle. The bias they found, while real, was far too small. That 0.2% effect is a whisper, not a shout. If this were the only source of asymmetry in the early universe, it could not possibly account for the 1 in a billion surplus of matter we see today. It is off by a factor of many millions, so while Cronin and Fitch proved the mirror could be broken, they also proved that the crack they found was not the one that saved the universe. The true engine of our existence remained hidden, a force with a much stronger hand, still waiting to be discovered in the shadows of the early cosmos. So the hunt turned to our most powerful map of reality, the Standard Model of particle physics. This extraordinary theory, which describes all known fundamental particles and forces except gravity, had to have an answer. It had already successfully incorporated the weak force and its quirky behavior, so surely it could account for the matter-antimatter imbalance. Within its elegant equations, physicists found the mechanism, a complex piece of mathematics called the Kabibbo-Kobayashi-Maskawa matrix, or the CKM matrix for short. This isn't some abstract concept, it describes a very real and strange property of the universe's building blocks. Think of the 6 types of quarks, the particles that make up protons and neutrons, not as stable, distinct breeds, but as flavors that can subtly mix and change. When quarks interact via the weak nuclear force, they don't always stay the same. A down quark can temporarily become a strange quark, or a bottom quark can shift into a top quark. The CKM matrix is essentially the recipe book for these transformations, detailing the probabilities of one quark turning into another. And crucially, woven into the complex numbers of this matrix is the possibility for CP violation. The transformations for matter particles and their antimatter counterparts are not perfectly mirrored, meaning the weak force treats their journeys slightly differently. Here at last was a precise mathematical source for the bias Sakharov demanded, built right into the core theory of particle physics. It was a triumphant moment of understanding. The Standard Model didn't just allow for an asymmetry, it predicted one, but then came the calculations. When physicists crunched the numbers, using all the known parameters of the CKM matrix to simulate the conditions of the early universe, a chilling result emerged. The amount of CP violation, the size of the bias, was far too small. The asymmetry it generates is a mere whisper, a statistical flicker. Extrapolating back to the first second after the Big Bang, this mechanism could only produce a surplus of about 1 matter particle for every 10 billion matter-antimatter pairs. That is 10 billion times too small to explain the 1 in a billion surplus we actually have. The conclusion was shocking. The Standard Model, our most complete and successful theory of the physical world, can only create a universe that is essentially empty. It would produce a cosmos a billion times more barren than our own, a vast expanse with perhaps a single, lonely galaxy where we see hundreds of billions. This isn't a minor discrepancy, it is a catastrophic shortfall. The known laws of physics, as magnificent as they are fundamentally incomplete. They contain the seed of the answer, a proof of principle that such a bias can exist, but they lack the sheer power needed to write the story of our existence. The true author of our material universe remains at large, its signature hidden somewhere beyond the borders of our current knowledge. This leaves us with a staggering cosmic deficit, a gap in our understanding so vast it defines the frontier of physics. We can now put a precise number on the problem, and the figure is humbling. Throughout the observable universe, for every photon, every particle of light, there are roughly 6 baryons, the heavy particles of matter, for every 10 billion photons. This ratio, about 6 times 10 to the negative 10th, is the fingerprint of our material reality, the final balance after all the annihilations were complete. It is the measurable surplus that built everything. Now, take that number and compare it to the best prediction our crown jewel theory can muster. When physicists calculate the amount of matter the Standard Model's known processes could have possibly created in the early universe, the answer is a number closer to 10 to the negative 18th. The difference between these two figures is not a minor rounding error, it is an abyss. It is the difference between a universe brimming with hundreds of billions of galaxies and a cosmos so empty it might contain only a single, isolated star system in the entire observable volume. This is the Baryon asymmetry problem, and it is not a quiet puzzle for specialists. It is one of the most profound and unambiguous failures of our current understanding. The standard model, for all its predictive power and beauty, falls catastrophically short. It whispers where the universe shouts. This gap is not a sign that the theory is wrong in its domain, but a glaring beacon pointing to something missing, a vast territory of new physics that must exist just beyond its edges. The first second of the universe required a far stronger hand, a force or a particle or a set of rules we have not yet discovered, to decisively tip the scales and write the abundance of our world into being. This gap in our understanding forces us to look for a stronger hand, a suspect with both motive and means. Our investigation now turns to the most ghostly particles in existence, neutrinos. These are the ultimate cosmic phantoms, trillions of which pass through your body every second without a trace, interacting so rarely they seem to barely inhabit our material reality at all. Yet their very elusiveness makes them a perfect candidate for rewriting the story of the early universe. To understand why, we must first confront a strange and beautiful possibility. What if a neutrino is its own opposite? In our everyday experience, every particle has a distinct antimatter twin. But a theoretical framework proposed by the physicist Eta Majorana suggests that for certain neutral particles, this duality might not exist. A Majorana particle would be its own antiparticle, a single entity that is both matter and antimatter at once. If neutrinos are Majorana particles, it would solve several deep puzzles at once, including the profound mystery of why they have such inexplicably tiny masses. But the implications stretch far beyond particle properties. This identity crisis at the heart of the neutrino could be the very engine that saved the cosmos. This leads us to an elegant and powerful theory called leptogenesis. Imagine the universe in its first searing moments, filled with unimaginable energy. In this chaos, there could have existed heavy, right-handed neutrinos, hypothetical cousins to the ghostly ones we detect today. These heavy neutrinos would have been unstable, destined to decay. And if they are Majorana particles, the decays would not have been symmetrical. The subtle physics of their interactions could have favored the production of ordinary leptons, like electrons and neutrinos, over their antimatter counterparts. In this scenario, a profound asymmetry is born not in the realm of quarks and baryons, but in the lighter family of particles called leptons. For a moment, the universe would have had an imbalance of leptons over antileptons. But we live in a universe of baryons, of protons and neutrons. How does a lepton surplus become our matter surplus? The answer lies in a remarkable and subtle dance encoded in the standard model itself. Through a class of interactions so delicate they are called Sphaleron processes, a lepton asymmetry can be transmuted, converted step by step into a baryon asymmetry. It is as if the universe first wrote the bias in invisible ink, in the ghostly ledger of neutrinos, and then used a cosmic chemistry to transfer that signature onto the heavier, more permanent building blocks of atoms. This theory is breathtaking in its scope. It connects the almost imperceptible mass of the neutrino, a number so small it defies intuition, directly to the grandest fact of our existence, the abundance of galaxies. It makes these silent, passing ghosts the prime architects of all structure. The hunt for evidence is now a global scientific pursuit, with experiments deep underground searching for a telltale signal called Neutrinoless double beta decay, a fingerprint that would prove the neutrino is its own antiparticle. Finding it would not just solve a particle mystery, it would point directly to the mechanism that populated the cosmos with something rather than nothing. The ghostly neutrino is not the only suspect capable of such a cosmic crime. To find a more powerful source of asymmetry, we must journey back to a time of almost inconceivable energy, when the universe was less than a trillionth of a second old. At these scales, our familiar world dissolves into something far more unified and strange. Today, we experience nature through four distinct forces. Gravity shapes the cosmos, electromagnetism binds atoms and gives us light, the strong force glues atomic nuclei together, and the weak force drives radioactive decay. But in that first, unimaginable flash, physics suggests these forces were not separate at all. They were different facets of a single, pristine superforce. This is the realm of grand unified theories, or GUTS, and they offer a breathtakingly elegant stage for creating our material universe. These theories propose that the electromagnetic, weak, and strong forces were once perfectly merged. As the newborn cosmos expanded and cooled at a frantic pace, this perfect symmetry began to crack. Think of it like water freezing into ice. As the temperature drops, the smooth, uniform liquid undergoes a phase transition, its symmetry breaking to form structured, crystalline ice. In a similar cosmic freezing, that single, unified force splintered into the three distinct forces we know today. But this transition was not a quiet event. It was a seismic shift in the fabric of reality itself, and it would have unleashed a storm of particles unimaginably heavy and fleeting, predicted by the math of these grand theories. They are known as X and Y bosons. These X and Y bosons are the key suspects. They would have been incredibly massive, carrying energies that make the collisions in our largest particle accelerators look like gentle taps. And crucially, their decays would have played by different rules. In our cool, modern universe, the number of baryons, the heavy matter particles, is essentially conserved. You cannot just create a proton from nothing, but in the searing heat of grand unification, that rulebook was not yet written. The decays of these X and Y bosons could have openly violated baryon number conservation on a monumental scale. They would not have created matter and antimatter in perfect, annihilating pairs. Instead, their breakdown could have had a built-in preference, a powerful bias that produced just a little more matter than antimatter every time one of these giants vanished. Picture this process unfolding everywhere in the infant cosmos, a frenzied decay of super-heavy particles as the unified force splinters. Each decay acts like a tiny, weighted coin toss, slightly favoring matter. And because these particles were so abundant in that energetic soup, the effect would not have been a faint whisper, but a resonant drumbeat. When the storm finally subsided and the last X-boson decayed, the universe would have been left with a permanent, baked-in surplus of quarks over antiquarks, a legacy written directly into the cooling plasma. This is a profoundly compelling solution. It ties the origin of all matter directly to one of the most fundamental events in cosmic history, the breaking of the forces themselves. The asymmetry is not a minor footnote, but a direct signature of a deeper, more unified reality. The challenge, of course, is that the energy required to produce an X or Y boson is so astronomically high that we could never hope to create one in a laboratory on Earth. We see their potential shadow in the universe they left behind, a cosmos filled with matter, waiting for us to decode the clues. But the grand unification of forces is not the only stage where a stronger bias could have played out. Our investigation leads us to a theory of breathtaking mathematical beauty, one that proposes a hidden symmetry so deep it could rewrite the entire particle ledger. This is supersymmetry, often called SUSY, and it suggests a profound doubling of the cosmic cast. The idea is elegantly simple, yet its implications are universe-altering. For every known particle in the Standard Model, from the familiar electron to the elusive neutrino, supersymmetry predicts a heavier, undiscovered superpartner. The electron's partner is the selectron, the quark's partner is the squark, the photon's partner is the photino. This is not just adding more particles to a list, it is proposing a fundamental mirroring between the two great families of the quantum world, the force-carrying particles and the matter particles. It is a symmetry of a higher order, one that could solve several of physics' deepest puzzles at once, from the nature of dark matter to the stability of the Higgs boson's mass. But for our story, its most compelling role is as a potential powerhouse for creating matter. In the furnace of the early universe, these superpartners would not have been exotic rarities, they would have been abundant. Particles like the neutrino, the superpartner of the neutrino, or the Neutrinoless, a mixture of several superpartners, would have been born in the chaos. And crucially, their interactions and decays would have operated under new rules, governed by forces we have not yet witnessed. These rules could have contained sources of charge parity violation far more potent than anything the standard model can offer. Imagine the decay of a heavy neutrino. In a supersymmetric cosmos, such a decay would not be a simple, mirrored event. The complex mathematics of the theory allows for scenarios where these superpartners decay into ordinary matter with a significant built-in preference, a strong bias that consistently produces more quarks than antiquarks or more leptons than antileptons. This is not the faint whisper of the kaon, but a resonant, commanding voice that could easily generate the 1 in a billion surplus we require. The early universe, filled with these heavy, decaying superpartners, would have been a factory for asymmetry, imprinting a matter-favoring signature across the entire cosmos as it cooled. The hunt for these shadow particles is one of the great quests of modern science. For decades, experiments at colliders like the Large Hadron Collider have searched for the telltale energy signatures of a selectron or a squark. So far, the superpartners have remained hidden, suggesting that if they exist, they are much heavier than initially hoped. Yet, their absence has not killed the theory, it has simply raised the energy bar. Future colliders designed to probe realms of even higher energy may finally reveal this hidden layer of reality. Discovering a single superpartner would be a revolution on par with the discovery of the Higgs boson, but it would be just the beginning. It would open the door to measuring their properties, to testing how they decay, and to searching within those decays for the precise, powerful mechanisms of charge parity violation that our universe so desperately needed. Supersymmetry offers a complete toolkit, a way to bridge the catastrophic gap between the standard model's feeble prediction and the abundant reality we inhabit. It turns the mystery of our existence from a haunting question into a potentially solvable equation, waiting for the right experiment to illuminate the numbers. But a powerful asymmetry in the laws of physics is only half the story. To build a universe that delicate, 1 in a billion surplus had to survive, and it had to be spread everywhere with perfect uniformity. This brings us to one of the most dramatic events in cosmic history, the epoch of inflation. In its first fleeting moments, the universe is thought to have undergone a period of exponential, faster-than-light expansion, stretching a subatomic speck of space to a size larger than our entire observable cosmos in an instant. This concept of cosmic inflation is not just about size, it is about preservation and distribution. It acts as the ultimate delivery system for our material reality. The timing of when our matter surplus was created relative to this great stretching becomes a critical piece of the puzzle. If the processes of baryogenesis, the birth of the matter asymmetry, happened before or during inflation, then a single, microscopic region where the bias played out would have been stretched to cosmic proportions. Imagine a single drop of ink falling into a vast ocean just before that ocean is instantly expanded to fill a galaxy. That one drop would color the entire expanse a uniform, faint hue. In this scenario, the entire observable universe inherits the same initial conditions, the same precise level of matter excess from that one original event. This explains the breathtaking uniformity we see in the cosmic microwave background, the ancient light from the infant cosmos, which shows a nearly perfect temperature in every direction we look. The matter that would later form every galaxy was imprinted with the same signature at the very beginning. However, if baryogenesis occurred after inflation ended, the story becomes more complex. After inflation, the universe was divided into countless causally disconnected patches, regions of space that had expanded so far apart that light, and therefore any influence, could not have traveled between them. They were isolated islands in the newborn cosmos. For our universe to have the same matter-to-antimatter ratio everywhere we look, the bias would have had to happen independently and produce exactly the same result in every single one of these trillions of isolated patches. This requires a law of physics so powerfully and universally biased that it forces the same outcome everywhere, like a loaded die that always rolls a 6 no matter who throws it or where. The question of timing, therefore, is not a minor technicality. It ties the fate of the entire cosmos directly to the mechanics of particle decay. It asks whether our material abundance was a single, unique quantum event magnified to a cosmic scale, or the inevitable output of a law so strong it stamped its preference onto every corner of reality simultaneously. This connection shows that the large-scale architecture of the universe, its smoothness and structure, is inseparably woven with the microscopic details of particle interactions. The journey to find the true source of our existence must navigate not just what broke the symmetry, but when and how that moment was frozen into the fabric of everything we see. The search for that stronger hand now moves from theory into the tangible world of steel, magnets, and monumental engineering. To test these grand ideas, we cannot simply look back in time, we must recreate it. This is the role of our greatest particle colliders, like the Large Hadron Collider, which act as our most powerful time machines. By accelerating protons to within a whisper of light speed and smashing them together, we can, for a fleeting fraction of a second, concentrate energy densities not seen since the universe was less than a billionth of a second old. Within the debris of these microscopic collisions, we hunt for echoes of the processes that may have decided our fate. The strategy is one of exquisite precision. Scientists don't just watch for spectacular explosions, they perform forensic accounting on the most subtle outcomes. A prime focus is on particles known as B-mesons and their antimatter twins, anti-B-mesons. These are unstable particles containing a bottom quark, and they are perfect laboratories for testing the mirror of reality. Created in the collisions, these particles live for just a trillionth of a second before decaying into showers of other, lighter particles. The entire experiment hinges on counting. Teams of researchers using detectors the size of cathedrals meticulously track and compare these decay patterns. They count how often a B-meson decays into a specific set of products, and then they do the same for the anti-B-meson. According to the Standard Model and its CKM matrix recipe book, there should be a tiny, predictable difference in these rates, a known amount of CP violation. The hunt is for any deviation from this prediction, any extra imbalance that cannot be explained by the known laws. Imagine it as checking a cosmic scale that should be perfectly balanced to 1,000th of a gram. If we find it is off by even a millionth of a gram more than our calculations predict, that discrepancy is everything. It is a direct signal, a fingerprint left at the scene, pointing to a new particle or a new force that participated in the decay, one that carries a stronger bias than anything in our current model. Such a discovery would not just be another data point, it would be a roadmap. It would tell physicists exactly where to look, at what energy, and for what kind of interaction to find the true source of the universe's material abundance. These high-precision experiments are our most direct line to the first moments, a way to interrogate the laws of physics under conditions that mimic the birth of everything. Every collision is a question posed to the universe, asking it to reveal the hidden clause that wrote our existence into being. While our largest machines recreate the universe's violent birth, other experiments listen for its quietest whispers. Far from the roaring collisions of particle colliders, the search for answers descends into the deep, silent heart of the Earth. In abandoned mines beneath mountains and in vast subterranean caverns, scientists have built laboratories dedicated to an almost meditative form of observation. These are places of profound stillness, shielded by thousands of feet of solid rock from the constant rain of cosmic rays that bombard our planet's surface. Here, in the near-perfect quiet, detectors of exquisite sensitivity wait, not for a spectacular explosion, but for a single, telltale flicker of light or a minute change in electrical charge. They are hunting for one of the rarest events in the known universe, a process so elusive it may happen, on average, less than once in a century for a given lump of material. This is the search for Neutrinoless double beta decay, and its discovery would rewrite our understanding of reality at the most fundamental level. To grasp why this quiet hunt matters so much, we need to understand the process itself. Let's start with ordinary double beta decay, which is rare enough on its own. In some unstable atomic nuclei, the usual form of radioactive decay is blocked by the laws of quantum mechanics. The nucleus cannot simply spit out a single electron to become more stable. Instead, in a kind of quantum workaround, two neutrons inside the nucleus can transform into two protons simultaneously, ejecting two electrons and two antineutrinos in the process. It is a coordinated, delicate dance that happens incredibly slowly. Now, imagine that same dance but performed in utter silence. In Neutrinoless double beta decay, the two antineutrinos never appear. They simply vanish from the equation. The only things that leave the nucleus are the two electrons, carrying away a very specific, precise amount of energy. This is not just a minor variation, it is a profound violation of a sacred rule. For the antineutrinos to cancel each other out, they must be able to meet and annihilate. And that is only possible if the neutrino and the antineutrino are, in fact, the very same particle. It would be the definitive proof that the neutrino is a Majorana particle, an entity that is its own opposite. This single observation would be a seismic event in physics. It would confirm a property of nature that has been a tantalizing possibility for decades, directly validating the idea that neutrinos could be the architects of our material universe through leptogenesis. If the neutrino is its own antiparticle, then the heavy, right-handed neutrinos proposed by that theory could have decayed with the powerful, matter-favoring bias needed to seed the cosmos. Finding Neutrinoless double beta decay would not show us that historical event directly, but it would provide the essential fingerprint. It would prove that the fundamental ingredient, the self-annihilating nature of the neutrino, is real. It is like finding a unique type of gunpowder at a modern crime scene, a powder that matches the residue found on a billion-year-old artifact. The connection, while indirect, would be overwhelmingly compelling. The experiments undertaking this search are marvels of patience and precision. Projects like Legend, using crystals of pure germanium cooled to near absolute zero, or NXO, which plans to use liquid xenon in a massive, pristine vessel, are designed to detect that one perfect signal amidst a sea of noise. They must shield against every possible interference, from the faint natural radioactivity in the surrounding rock to the subtle signals from cosmic rays that still penetrate the depths. They operate on timescales of years, accumulating data with relentless patience, knowing that the single event they seek could arrive tomorrow or not for another decade. This quiet, watchful science is the perfect complement to the explosive experiments at colliders. One approach tries to recreate the energy of the early universe to see what new particles emerge. The other listens with perfect stillness for a fundamental property of a particle we already know. Together, they form a complete strategy, a pincer movement to corner the truth about our origins. The silence of these deep laboratories is not an absence, but a focused intensity, a collective holding of breath as humanity, listens for a whisper from the moment everything began. While deep underground laboratories listen for whispers, other eyes are fixed on the endless rain from the cosmos itself. High above the Earth, mounted on the International Space Station, a 7-ton instrument called the Alpha Magnetic Spectrometer stares unblinkingly into the void. Its mission is not to see light, but to catch and identify the high-speed atomic fragments that constantly bombard our planet, particles known as cosmic rays. These are not just random debris, they are samples of distant astrophysical processes, messengers carrying information from across the galaxy. And within this torrent, scientists are hunting for a ghost, a relic so profound that finding even one would send shockwaves through cosmology. They are searching for anti-helium. To understand why this search is so critical, picture the aftermath of the Great Annihilation. Our leading theories suggest the process that favored matter was incredibly efficient, wiping out antimatter on a global scale and leaving that 1 in a billion surplus. But what if it wasn't perfectly uniform? What if, like oil and water refusing to mix, regions of matter and antimatter briefly separated in the searing plasma of the infant universe? In this scenario, vast domains of antimatter could have formed, isolated islands in a sea of matter. These antimatter domains would have gone through their own stellar evolution, with antistars forming in anti-galaxies, fusing anti-hydrogen into heavier elements like anti-helium in their cores. If such structures existed and somehow survived without contacting normal matter, their explosive deaths or stellar winds could, in theory, fling particles of anti-helium across intergalactic space. These particles would travel for billions of years as cosmic rays. This is what makes the hunt for a single anti-helium nucleus so monumental. Anti-helium cannot be produced in any significant amount by the mundane astrophysical processes we understand today. The collisions that create cosmic rays in our matter-dominated galaxy simply do not have the energy or the right ingredients to forge an intact anti-helium nucleus, which requires 2 antiprotons and 2 antineutrons to bind together. Finding one would be like finding a perfectly preserved coin from a lost civilization in the middle of an empty desert, a clear artifact that could not belong to the local environment. It would be direct, tangible evidence that pockets of primordial antimatter not only existed but endured long enough to build complex structures, challenging the idea of a perfectly uniform asymmetry. The Alpha Magnetic Spectrometer has been analyzing this cosmic rain for over a decade, sorting through more than 200 billion particles. So far, it has seen no convincing anti-helium. This profound absence is itself a powerful piece of data, reinforcing the model of a cosmos that was asymmetric from its very first moments on the largest scales. It suggests that if antimatter domains ever existed, they were either completely annihilated or are so unimaginably distant that their messengers have not reached us. Yet the search continues, a testament to patience on a cosmic scale. Every detection, every negative result tightens the constraints on our theories, telling us what the early universe could not have been. The instrument keeps watching, a silent sentinel in orbit, sifting through endless streams of ordinary matter for that one extraordinary anomaly, a single particle that could force us to redraw the map of cosmic history. While we search the cosmos for anti-helium and listen deep underground for silent decays, one of the most direct tests of all is happening right here on Earth, and it asks a question so basic a child could pose it. Does antimatter fall down? The answer seems obvious, even trivial. Of course it must fall down, just like everything else. Gravity, we are taught, treats all mass equally. This principle, known as the weak equivalence principle, is a cornerstone of Einstein's theory of general relativity and is baked into our very understanding of the cosmos. An apple and a rock, regardless of their composition, will accelerate toward the Earth at the same rate if dropped from the same height. So why would an anti-apple be any different? Yet this simple assumption has never been directly tested with neutral antimatter, and that gap in our knowledge represents a thrilling vulnerability in our models. If antimatter were to behave differently under gravity, if it fell upward or even just at a slightly different rate, it would not be a minor curiosity. It would be a crack in the foundation of modern physics, a discovery that could reshape our entire narrative of cosmic origins. The quest to perform this test is a story of breathtaking ingenuity, centered on an experiment with a deceptively simple name, a LPH-G, at the CERN laboratory in Switzerland. The goal sounds straightforward: create the simplest antimatter atom, anti-hydrogen, trap it, and then let it go to see which way it moves. But each of those steps is a monumental challenge. Anti-hydrogen is a neutral atom made of an antiproton and a positron, the antimatter versions of a proton and an electron. Because it has no net electric charge, you cannot hold it in place with the convenient electromagnetic traps used for charged particles. The LPH team had to invent a completely new kind of bottle, a magnetic trap shaped like a long, thin tube, using incredibly precise magnetic fields to confine the anti-atoms. They cool these atoms to within a fraction of absolute zero to slow their frantic motion, creating just enough stillness to attempt the measurement. Then, the most delicate part, they slowly turn off the magnetic fields at the top and bottom of their trap. It is a cosmic coin toss happening in a vacuum chamber. The anti-hydrogen atoms are released, and in that moment of freedom, they must make a choice pulled by the gravity of the Earth below. Do they fall or do they rise? Detecting this tiny movement is a feat of precision engineering. The experiment is housed in a vertical shaft, and as the atoms are released, sensitive detectors along the walls look for the telltale flash of light that signals an annihilation. The moment an anti-hydrogen atom touches the ordinary matter of the apparatus and is destroyed. By mapping where along the shaft these annihilations occur most frequently, the scientists can reconstruct the path the atoms took. Did they mostly drift downward, annihilating near the bottom? Or did they float upward? The implications of finding any deviation are staggering. Gravity is the one fundamental force not yet incorporated into our quantum understanding of particles. If antimatter couples to gravity differently, it suggests a deep and previously hidden connection between gravity and the quantum properties that distinguish matter from antimatter. For the mystery of our existence, this could open a radical new avenue. Perhaps in the extreme gravity of the early universe, this differential response played a role in separating matter from antimatter, like shaking a pan to separate grains of different densities. If antimatter experienced a slight gravitational repulsion, it could have been pushed into different domains, making the great annihilation less than perfectly efficient and leaving behind isolated pockets of survivors. The first results from the LPH-G experiment, announced in late 2023, sent a wave of relief and fascination through the physics community. Within the precision of their measurement, anti-hydrogen does indeed fall down. It does not levitate or rise, for now the universe continues to play by the rules we expected. But this is not the end of the story. It is the beginning of a new era of precision. The initial measurement, while groundbreaking, still has a margin of error. The next phase is to tighten that margin to see if antimatter falls at exactly the same rate as matter, to within 1 part in 100, then 1 part in 1,000, and beyond. Any tiny deviation, any hint that the acceleration is not precisely 9.8 meters per second squared for antimatter, would be a signal as bright as a supernova. It would mean that gravity, the force that sculpts galaxies and bends the path of light, also carries within it a subtle preference, a bias that could have written the first line of our cosmic story. So this seemingly simple question, does antimatter fall, connects directly to the grandest mystery of all. It probes the last untested frontier of the equivalence principle, seeking any whisper of a difference in how the universe treats something and its opposite. In the quiet descent of a single anti-atom, we might yet find the signature of a force that chose long ago to build a world. The hunt for a deeper bias in nature leads us to a mystery that is both elegant and profoundly unsettling. It is called the strong CP problem, and it reveals a startling gap in our understanding of the very force that holds atomic nuclei together. The strong nuclear force, described by a theory called quantum chromodynamics, is the most powerful glue in the universe, binding quarks into protons and neutrons. Its mathematics are exquisitely precise, but they contain a hidden door, a parameter that theorists call theta. This theta parameter is a dial, and turning it would introduce a specific type of charge parity violation directly into the strong force. The mathematics say this dial could be set to any value from 0 to 360 degrees, and the theory would still work, but here is the cosmic puzzle. Every experiment we have ever done tells us this dial is not just turned down low, it is set to 0 with a precision that borders on the miraculous. Measurements of the neutron's electric dipole moment, a test of how its positive and negative charges are distributed, show no sign of the twisting effect that a non-zero theta would produce. The observed violation is at least 1 billion times smaller than the theory naively allows. It is as if we discovered a fundamental law of physics contained a powerful switch that could drastically change the world, yet we find it permanently and perfectly locked in the off position. This is not a minor detail. It feels like a cosmic conspiracy, a fine-tuning so extreme it demands an explanation. Why is the strong force so perfectly respectful of this symmetry when every other part of nature suggests such perfect mirrors are meant to be broken? The most compelling answer to this riddle is not an adjustment to the mathematics, but the prediction of an entirely new particle, one of the most fascinating hypothetical entities in all of physics, the action. Proposed in the 1970s, the action is a conceptual masterstroke. The idea is that this theta dial is not a fixed number, but a field that permeates all of space like the Higgs field. The action is the quantum ripple in that field. Through its subtle interactions, this field naturally relaxes to 0, dynamically solving the strong CP problem without any need for fine-tuning. The action would be a cosmic peacemaker, quietly enforcing symmetry in the strong force. But the consequences of such a particle are anything but quiet. Because of the way it emerges from this profound puzzle, the action is predicted to be incredibly light, possibly billions of times lighter than an electron, and to interact with ordinary matter only very, very weakly. It would be a ghost even more elusive than the neutrino, and this is where the connection to our greatest cosmic mysteries becomes breathtaking. In the hot, dense conditions of the early universe, actions would not have been rare curiosities. They would have been produced in staggering numbers, a cosmic fog of these ultra-light particles. As the universe expanded and cooled, this action fog would not have annihilated or decayed away. It would have simply persisted, drifting through the cosmos, unaffected by light or the strong nuclear force, interacting only through gravity and the faintest of whispers. This description should sound familiar. A form of matter that is abundant, invisible, does not emit or absorb light, and shapes the cosmos through its gravity alone. That is the exact definition of dark matter. The action, born from a puzzle about symmetry in the strong force, emerges as a prime candidate to explain the 85% of the universe's matter that we cannot see. This is a connection of stunning beauty. It suggests that the question of why matter dominates over antimatter and the question of what dark matter is made of may not be separate puzzles at all, but different facets of a single, deeper truth. The action serves as a potential bridge, a theoretical thread tying together the visible imbalance we are made from and the invisible scaffolding that holds galaxies together. The search for the action is now a major frontier, with experiments using powerful magnetic fields and ultra-sensitive detectors, listening for the faintest conversion of an action into a microwave photon. Finding it would be a double revelation, solving one of particle physics' most annoying fine-tuning problems while simultaneously illuminating the dark heart of the cosmos. It would tell us that the forces that wrote our existence into being also wove the hidden skeleton of the universe, a single, elegant answer to two of reality's deepest and most persistent whispers. This search for a deeper physical law is not the only way to confront the mystery. There exists a line of reasoning that shifts the question entirely, moving from how the universe works to why we are here to ask the question at all. This is the Anthropic Principle, and it stands as one of the most provocative and debated ideas in modern cosmology. At its heart is a simple, almost tautological statement: the universe we observe must be compatible with the existence of observers. The constants of nature, from the strength of gravity to the mass of the electron, appear finely tuned. If they were even slightly different, stars would not ignite, atoms would not bond, and life as we know it would be impossible. The matter-antimatter asymmetry fits perfectly into this puzzle. That 1 in a billion surplus is not an arbitrary number, it is a precise requirement. If the asymmetry had been 0, the universe would have annihilated itself into darkness. If it had been significantly larger, say 1 in 1,000, the early cosmos would have been so dense with matter that it would have collapsed back on itself long before stars could form. Our existence hinges on that narrow, golden window. The Anthropic Principle asks us to consider a staggering possibility. What if our universe, with its specific laws and its specific asymmetry, is not unique? This is the concept of the multiverse. Imagine a vast, perhaps infinite, cosmic landscape where different regions, different bubble universes, have different physical laws and different fundamental constants. In some bubbles, the asymmetry is 0, and those universes are dark and empty. In others, the asymmetry is too large and they collapse instantly. We find ourselves, inevitably, in one of the rare bubbles where the numbers lined up just right to allow for galaxies, planets, and eventually, creatures who can look up and wonder why. This perspective is controversial because it feels, to many scientists, like an explanation that explains nothing. It does not point to a new particle or a new force. It does not provide a dynamic mechanism we can test in a lab. It frames the asymmetry not as a puzzle to be solved by physics alone, but as a necessary condition, a cosmic prerequisite for observation. We are here because this is one of the few places we could possibly be. Proponents argue it is a logical necessity when confronting fine-tuning, a way to make sense of incredible coincidences without invoking a designer. Critics see it as a philosophical surrender, a stopping point for inquiry that could discourage the search for a deeper, testable theory. Yet, even as a controversial interpretation, it serves a vital purpose. It sharpens the question. It forces us to ask whether the answer we seek is a unique, dynamic process waiting to be discovered within our universe, or whether we are sampling one possibility from a much vaster, perhaps untestable, ensemble of realities. The Anthropic Principle does not close the investigation. It expands the frame, reminding us that the mystery of our material existence is intertwined with the deepest questions of reality itself. Beyond the elegant symmetries of supersymmetry and grand unification, the landscape of possible answers grows even more exotic. Theoretical physics is a realm of boundless creativity, where scientists construct entire universes from mathematics, searching for the one blueprint that matches our own. Among these more speculative designs lies a class of theories with a distinctly industrial name, Technicolor. The idea is as bold as it sounds. In our standard model, particles acquire mass through their interaction with the Higgs field, a kind of cosmic molasses that fills all of space. Technicolor proposes a radically different origin story. It suggests that at very high energies, a new, powerful force emerges, one that behaves much like the strong nuclear force that binds quarks. This force would bind new, hypothetical particles called technoquarks into composite objects, and the dynamics of this binding would spontaneously break electroweak symmetry, giving mass to particles without the need for a fundamental Higgs boson. It is a universe where mass is not granted by a passive field, but forged in the furnace of a new interaction. This architectural shift opens a door. Within the complex dynamics of a Technicolor force, the conditions for generating a matter asymmetry could be dramatically different. The new interactions between technoquarks and their own antiparticles could contain sources of charge parity violation far richer and more potent than anything in the standard model. The early universe, seething with this exotic force, could have produced our matter surplus through a completely different choreography, one written in the language of a strength we have not yet witnessed. While the discovery of the Higgs boson in 2012 made the simplest versions of Technicolor less likely, the core idea remains a testament to theoretical ingenuity. It represents a path not taken by nature, at least in its original form, but it underscores a vital truth about the search. Scientists are not just testing one or two favorite ideas, they are exploring the entire library of mathematical possibility. From extra-spatial dimensions curled into vanishingly small loops, to theories where every particle is a vibrating string in a 10-dimensional reality, the models grow more abstract and wondrous. Each framework provides a new stage on which the drama of baryogenesis could have played out. Each offers different actors, new forces, and unique scripts for how a bias could be written into the laws. Some models propose that the asymmetry was not created in the hot Big Bang at all, but was imprinted by the decay of fields driving cosmic inflation. Others suggest it emerged from the violent collisions of bubbles of spacetime as the universe underwent a phase transition. The sheer breadth of this exploration is breathtaking. It shows a scientific community willing to follow the evidence wherever it leads, even into realms that seem like pure science fiction. The final answer to why we exist may not come from a minor tweak to our current map, but from a completely unexpected direction, from a mathematical structure we have only just begun to glimpse. This relentless, creative probing is our greatest asset. It ensures that no stone is left unturned in the quest to understand the universe's profound and mysterious preference for something over nothing. Sakharov's second demand is the most radical of all, challenging a law we once thought was absolute. The total number of matter particles in the universe, the Baryon number, must not be a fixed, sacred total. It must be a number that can change. For our surplus to emerge from nothing, the early cosmos needed a way to write a permanent credit into an account that began at zero. This requires processes that actively violate Baryon number conservation, interactions where matter can be created or destroyed not through annihilation with antimatter, but fundamentally from the raw fabric of reality itself. Within our current standard model, such processes are not entirely forbidden. The mathematics allow for them, but they are hidden behind a barrier so immense it renders them practically mythical. They are predicted to occur, but with a probability so vanishingly small that across the entire lifetime of the observable universe, they might only happen a handful of times. This makes them, for all practical purposes, invisible to us, a ghostly possibility written into the equations but never witnessed in the lab. The ultimate test, the canonical example of such a violation, is the decay of the proton. We are taught that protons are stable, the eternal building blocks of atomic nuclei. But if Baryon number is not perfectly conserved, then even the proton must eventually succumb to decay. It would not explode but quietly, through some exotic quantum tunnel, transform into lighter particles, perhaps a positron and a neutral pion, effectively erasing a fundamental piece of matter from the universe. Finding proton decay would be the smoking gun, direct proof that Sakharov's second condition is not just theoretical, but a real feature of our world. For decades, scientists have been listening for this whisper. Experiments like the magnificent Super Kamiok and in Japan use colossal tanks of ultra-pure water, buried deep underground to shield from cosmic noise, lined with thousands of sensitive light detectors. They monitor the equivalent of trillions upon trillions of protons, watching for the single, characteristic flash of light that would signal one of them spontaneously coming apart. They have watched with incredible patience for over 30 years, and so far they have seen nothing. The proton, if it decays at all, does so with a half-life longer than 10 to the 34 years, a number so vast it dwarfs the current age of the universe by many orders of magnitude. This profound silence is not a failure, it is a crucial piece of data. It tells us that if the proton does decay, it does so far more slowly than the simplest grand unified theories predicted. This non-observation has eliminated entire families of elegant models, forcing theorists to build more complex and nuanced visions of unification. The continued search, however, is unwavering. New, even larger detectors are being planned because the stakes could not be higher. Observing a single proton decay would do more than just win a Nobel Prize. It would crack open a window into physics at energies we can never hope to reach on Earth, confirming that the laws do permit the fundamental creation and destruction of matter. It would prove that the universe possesses, however faintly, the very mechanism needed to tilt the scales from perfect symmetry to our material abundance. Until that day comes, the silence of the proton is a reminder of just how perfectly the early universe had to be engineered to leave behind a world like ours. The numbers we measure today are the final verdict on any theory of our origins. While particle physics seeks the microscopic mechanism, astrophysics provides the cosmic scale, delivering the precise, observational target that any successful explanation must hit. The most powerful evidence comes from the oldest light in the universe, the cosmic microwave background radiation. This faint, cold glow is the afterimage of the Big Bang, a snapshot of the cosmos when it was just 380,000 years old, a time before the first stars ignited. Imprinted in the subtle temperature variations of this radiation, like a fossilized fingerprint, is a precise record of the universe's composition at that infant stage. By analyzing these patterns with satellites like Planck, cosmologists have performed a kind of cosmic accounting. They can measure the density of ordinary matter, the baryons, to an astonishing precision of about 1%. That number, the baryon density, is the golden ratio. It is the exact amount of surplus matter that survived the Great Annihilation, the raw material budget from which every galaxy was later built. Any theory that claims to explain our existence, whether through leptogenesis, grand unification, or supersymmetry, must ultimately produce this exact number from its equations. It is the finish line written in the sky. This cosmic census is complemented by the large-scale architecture of the universe itself. When we map the distribution of galaxies across billions of light-years, we see a vast, intricate cosmic web, filaments of matter stretching between immense voids. The gravitational pull required to sculpt this structure over cosmic time also tells us how much ordinary matter is present. This independent measurement aligns perfectly with the story told by the ancient light, confirming the baryon density from a completely different angle. Together, they form an unshakable observational pillar, a fact about our reality that is as solid as the ground beneath our feet. There is another, more dramatic test written across the heavens, a search for something that is profoundly absent. If sizable domains of primordial antimatter had survived into the modern era, there would be frontiers, boundaries where these seas of matter and antimatter meet. At such a border, even the sparse gas floating between galaxies would occasionally drift across the line. A lone atom of hydrogen wandering into an anti-galaxy would meet its antiparticle, resulting in annihilation. These encounters would produce a very specific signature, a burst of gamma rays with a characteristic energy. Astronomers have scanned the sky meticulously for this telltale radiation. They have looked at the diffuse glow between galaxy clusters and across the seemingly empty voids. The result is a resonant silence. No such annihilation glow has been found. The absence of this signal speaks volumes. It strongly suggests that our entire observable universe, a sphere nearly 100 billion light-years across, is composed almost entirely of matter. Any surviving antimatter must be confined to speculative, isolated regions far beyond our cosmological horizon, realms so distant that their light or their annihilation signals have not had time to reach us in the entire history of the cosmos. This negative evidence is as powerful as a positive detection. It tells us that the process that favored matter was not a local fluke in our neighborhood, but a global phenomenon that shaped everything we can possibly see. The cosmos itself, through its ancient light, its grand structure, and its silent frontiers, is bearing witness to the same profound mystery we seek to solve in our laboratories. The silence of the proton is a powerful constraint, but it is not the end of the road. It simply tells us that the energy required to see the true architects of our existence is far beyond what our current tools can muster. The Large Hadron Collider, a marvel of human engineering that revealed the Higgs boson, operates at an energy frontier of 13 tera-electron volts. This is an astounding achievement, recreating conditions a fraction of a second after the Big Bang. Yet, to probe the moments where grand unified forces reigned or supersymmetric particles danced, we may need to reach energies 100 times higher or more. The particles that could decisively tip the cosmic scales likely reside at these distant frontiers, forever out of reach of our present machine. This is not a failure of imagination, but a call to build the next generation of time machines. The future of experimental particle physics is being drafted now in the form of colossal proposals. One vision is the Future Circular Collider, or FCC. Imagine a new tunnel carved beneath the European countryside, not 17 miles in circumference like the LHC, but a staggering 56 miles around. Within this underground racetrack, protons could be accelerated to energies of 100 tera-electron volts, smashing together with a force that brushes closer to the unification of forces. Another, even more ambitious concept is a muon collider. Muons are heavier cousins of the electron, and because they do not lose as much energy as protons do when racing around a ring, they could deliver cleaner, more focused collisions at unprecedented energies in a more compact space. These are not just bigger versions of what we have, they are qualitative leaps. What could such machines find? Their primary mission is to explore the terra incognita on our map of particle physics. They could directly produce new, heavy particles predicted by supersymmetry, catching a selectron or a neutrino in the debris of a collision. They could observe the Higgs boson, the particle that gives others mass, interacting with itself or with other particles with such precision that any deviation from the standard model's prediction would shine like a beacon, pointing to new forces or dimensions. They might even create rare, exotic states of matter that exhibit the kind of profound charge parity violation Sakharov's conditions demand. Each of these discoveries would be a clue, a piece of the puzzle falling into place. A new particle's properties, its decay patterns, its very existence, would tell us if we are on the right track with grand unification, or if the answer lies in a completely unexpected sector of reality. Building these machines is an endeavor of generations, requiring global collaboration and investment measured in the tens of billions. The questions they seek to answer, however, are literally cosmic in value. They represent humanity's stubborn insistence on looking deeper, on building a window into the first trillionth of a second of everything, hoping to catch a glimpse of the process that decided something over nothing. The journey from the profound silence of underground laboratories to the thunderous collisions of a future collider is all part of the same great inquiry, a testament to our need to understand not just the universe we inhabit, but why we are here to inhabit it at all. While we build larger colliders to reach higher energies, another revolutionary tool is being forged, one that operates on an entirely different principle. Quantum computing is not about brute force, but about harnessing the bizarre rules of quantum mechanics themselves to solve problems that would take classical computers longer than the age of the universe. The early cosmos was not just hot and dense, it was fundamentally quantum. Every particle, every force, every fluctuation was governed by the probabilistic, entangled, and non-intuitive laws that rule the subatomic realm. To truly simulate those first moments, to watch the asymmetry unfold in a digital recreation, we need a machine that thinks in quantum. Classical computers, the ones we use every day, process information in bits, simple switches that are either a 0 or a 1. They are brilliant at many tasks, but they hit a wall when trying to model complex quantum systems. A system of just a few hundred interacting quantum particles would require more classical bits to describe than there are atoms in the known universe. It is a computational dead end. Quantum computers leap over this wall. Instead of bits, they use quantum bits or qubits. A qubit can be a 0, a 1, or, and this is the magical part, a superposition of both states at the same time. It is like a coin spinning in mid-air, not heads or tails, but both possibilities simultaneously. Furthermore, qubits can be entangled, linked together so that the state of one instantly influences the state of another, no matter the distance. This allows a quantum computer to explore a vast landscape of possibilities in parallel. For the mystery of baryogenesis, this is a game changer. Theorists have proposed dozens of elegant models, from grand unified theories to leptogenesis, each with its own mathematical script for how matter won out. Testing these models requires solving the equations of quantum field theory under the extreme, dynamic conditions of the expanding early universe. On a classical computer, this is often impossible, forcing scientists to make simplifying approximations that might miss the very physics they are trying to study. A sufficiently advanced quantum computer could change that. Imagine programming a lattice of entangled qubits to represent the quantum fields that filled the infant cosmos. You would encode the starting conditions, a seething, symmetric plasma of energy. Then, you would instruct the machine to simulate the evolution of those fields as the universe expands and cools, following the precise mathematical rules of a candidate theory. You could introduce a hypothetical heavy neutrino and watch its decay. You could simulate the violent phase transition of a grand unified force, and you could observe, in real time within the quantum simulation, whether the final state of the system shows a net surplus of matter over antimatter. It would be a virtual universe in a box, a laboratory for genesis. The goal is not to create a perfect, full-scale replica of the Big Bang, but to capture the essential quantum dynamics of the asymmetry generating process. Did the simulated domain walls between different vacuum states produce a bias? Did the decay of your programmed X-bosons leave behind a measurable quark excess? The quantum computer could run the simulation thousands of times, providing statistical evidence for or against a particular model's viability. This is a profoundly new way of doing theoretical physics. It moves beyond pen and paper calculations and even beyond massive supercomputer approximations. It allows for experimentation on the laws of physics themselves. While today's quantum computers are still in their infancy, prone to errors and limited in the number of qubits they can coherently control, the trajectory is clear. Major research initiatives at laboratories like CERN and partnerships with tech companies are already exploring how to map problems in quantum field theory onto quantum hardware. Each year, the machines grow more stable and capable. the day may come when a crucial calculation, one that decides between two competing theories of our origins, is performed not in a notebook or on a silicon cluster, but in the entangled heart of a quantum processor. This tool offers a hope that is both humble and extraordinary, a way to witness the first act of our cosmic story by inviting the universe to perform it again, in miniature, right before our eyes. This investigation now reaches beyond our planet and our machines into the violent heart of distant cataclysms. A new era of astronomy is dawning, one that listens to the universe with more than just our eyes. We call it multi-messenger astronomy, and it combines the ancient language of light with the ghostly whispers of neutrinos and the ripples in spacetime itself, gravitational waves. Together, they form a complete sensory suite for the cosmos, allowing us to witness events so extreme they become natural laboratories, testing the very laws that might have built our world. Among the most powerful of these cosmic crucibles are the collisions of neutron stars, the dense, city-sized cores left behind after giant stars explode. When two of these ultra-dense objects spiral together and merge, they forge conditions of unimaginable pressure and magnetic fury, recreating for a brief moment a sliver of the universe's searing infancy. Within that maelstrom, theorists propose novel mechanisms for generating matter asymmetry could spring to life. One fascinating possibility is known as the chiral magnetic effect. In the presence of incredibly strong magnetic fields and a soup of ultra-hot, dense matter, the subtle differences between left-handed and right-handed particles could be dramatically amplified. This could drive currents that separate electric charge, effectively sorting matter from antimatter in the turbulent aftermath of the collision. If such a process occurs, it would not be a silent event. The unique fingerprint of this asymmetry production could be imprinted on the messengers fleeing the disaster. The flood of neutrinos generated in the merger could carry a specific pattern, a subtle skew in their energies or flavors that betrays the chiral magnetic effect at work. Even more remarkably, the gravitational waves, the ripples in the fabric of spacetime produced by the merging stars, might hold a clue. The precise shape of these waves, how they ring down after the final collision, could be minutely altered by the internal dynamics of the hot matter cloud, dynamics that include any charge-separating processes. This transforms a distant cataclysm into a real-time experiment. We are no longer limited to probing the homogeneous soup of the early universe. Instead, we can watch asymmetry potentially being forged in a specific, localized, and incredibly violent astrophysical setting. A single, well-observed neutron-star merger where we detect the light, the neutrinos, and the gravitational waves in concert could provide a dataset of unparalleled richness. By comparing the signals from these different messengers, we can search for inconsistencies, for hints that the event produced something more than our standard models predict. It broadens the investigation from recreating the past in a lab to observing the present in the cosmos. Every such cataclysm becomes a test, a chance to see if the laws that favor matter are merely a relic of a long-gone epoch, or an active, ongoing feature of reality, still writing its bias into the universe today in the most spectacular furnaces imaginable. The pursuit of this single number, that 1 in a billion surplus, is far more than a technical puzzle for physicists. It is a journey that reshapes our entire relationship with the cosmos, transforming the universe from a backdrop into a story with a beginning, a crisis, and a fragile, beautiful resolution. To solve this mystery would be to complete the most important chapter in our cosmic autobiography, connecting the formless symmetry of the Big Bang directly to the structured, material reality we inhabit today. It answers the ultimate how question of our existence, providing the physical mechanism that allowed something to emerge from what should have been nothing. This understanding would not diminish the wonder, it would deepen it, grounding the profound fact of our being in the elegant, if still hidden, laws of nature. This quest also brushes against the deepest philosophical currents. It asks why the universe is not just orderly but comprehensible. The very fact that we can formulate Sakharov's conditions, build experiments to test them, and use mathematics to model the first second of everything suggests a reality that is, at some level, intelligible. The mystery of the asymmetry sits at the crossroads of this intelligibility, a problem so precisely defined that its solution must lie within the reach of human reason and ingenuity. Furthermore, the specific outcome of that ancient bias, a universe with galaxies and stars, is a universe that allows for complexity, for chemistry, and ultimately for observers. It makes our investigation a self-referential loop, where a cosmos that permitted life now uses that life to understand its own origins. This isn't a teleological argument, but a recognition of a staggering chain of cause and effect written into the fabric of reality itself. The drive to solve this puzzle is a powerful engine for human progress. It pushes engineering to its absolute limits, demanding the creation of deeper underground laboratories, more sensitive detectors that can hear a single quantum whisper, and magnets of unimaginable precision to hold antimatter still. It fuels the development of quantum computers, machines that think in the language of the early universe itself. This technological fallout, from advanced computing to new materials, radiates out into society, improving medicine, communication, and our fundamental capacity to innovate. Just as importantly, the mystery inspires. It captures the imagination of students around the world, drawing new minds into science not with dry equations, but with a narrative of cosmic detective work, a real-life mystery about why we are here at all. It represents science at its most ambitious and unifying, a global, collaborative effort to answer a question that belongs to all of humanity. Ultimately, this is more than physics. It is the collective human project of seeking our own origin story. Every measurement in a deep mine, every collision in a vast tunnel, every line of code in a quantum simulation is part of a conversation we are having with the universe. We are asking it to reveal the reason for our material existence. The answer, when it comes, will not just fill a gap in a textbook. It will tell us something fundamental about the character of reality, about whether the laws that govern everything contain, at their very heart, a necessary inclination for structure, for complexity, and for the emergence of stories like ours in the vast cosmic dark. This cosmic story is often eclipsed by a more sensational fiction. In books and films, antimatter is the ultimate doomsday device, a glowing vial of pure destruction capable of annihilating planets. The trope is rooted in a kernel of truth, the 100% efficiency of matter-antimatter annihilation. The energy release is staggering, gram for gram, millions of times more potent than nuclear fission. But this raw potential has been wildly distorted into a fantasy of easy cosmic power and apocalyptic weapons, a distortion that obscures the profound and delicate reality. The truth is far more interesting and far less Hollywood. Creating even a single gram of antimatter is a monumental, perhaps insurmountable, engineering challenge. Facilities like CERN produce antimatter not by the gram but by the particle. Their most successful efforts have created and trapped mere billions of antiprotons. To put that in perspective, 1 billion antiprotons contains less than a billionth of a microgram of mass. At the current rate of production, it would take CERN many billions of years to make a single gram. The cost would be astronomical, requiring energy inputs far greater than what the antimatter could ever give back, and storage is its own nightmare. You cannot put it in a jar. Antimatter must be suspended in ultra-high vacuum magnetic traps, isolated from every atom of normal matter, a feat requiring immense power and precision just to hold a tiny cloud stable for minutes or hours. This is not a practical fuel, it is a scientific specimen of immense value. The antimatter that exists naturally around us is equally mundane, not monstrous. Positrons, the antimatter twins of electrons, are produced routinely in radioactive decay from elements like potassium-40, found in bananas and our own bones. They are created in the upper atmosphere when cosmic rays strike air molecules. These particles exist, they annihilate quietly with nearby electrons, and the process is utterly harmless, a background whisper of physics in action. The real terror is not antimatter itself, but its absence. The universe-destroying cataclysm already happened in that first second. What remains is the quiet, enduring aftermath. By separating the science fact from science fiction, we clear the stage for the genuine wonder. The mystery is not how to weaponize this elusive substance, but why it is so elusive to begin with. Why did the universe leave us with a world of matter and relegate its perfect mirror to the realm of cosmic ghosts and laboratory curiosities? That question holds a deeper power than any fictional bomb. The glow of a positron annihilation is not just a cosmic signature, it is a medical miracle. While physicists chase the ghost of primordial antimatter in deep mines and giant rings, the antimatter twin of the electron is at work in hospitals around the world every single day. This application comes in the form of the positron emission tomography scan, the PET scan, one of the most powerful diagnostic tools in modern medicine. The principle is a direct, beautiful application of antimatter annihilation. A patient is injected with a mildly radioactive tracer, a sugar molecule that has been tagged with a radioactive isotope. As this isotope decays, it emits a positron. That positron travels a minuscule distance through the body before it inevitably meets an electron. They annihilate, converting their mass into energy and producing two gamma-ray photons that shoot off in opposite directions. A ring of sensitive detectors surrounding the patient picks up these paired photons, and a computer uses their arrival points to triangulate exactly where inside the body the annihilation occurred. By mapping the density of these events, doctors can create a stunningly detailed three-dimensional image of metabolic activity. Cancerous cells, which are metabolically ravenous and consume sugar at a much higher rate, light up like beacons on the scan. The same technique illuminates blood flow in the heart and reveals the patterns of brain function in neurological disorders. This is not a distant future technology. It is a present-day reality born from our understanding of a fundamental particle. The positron, once a theoretical curiosity and a clue to a broken cosmic mirror, is now a life-saving tool. It transforms the abstract concept of matter-antimatter annihilation into a procedure that offers clarity, guides treatment, and provides hope in the face of serious illness. This direct line from a cosmic mystery to a hospital room is a profound reminder that the pursuit of pure knowledge often yields the most practical gifts. The engineering required to even ask the universe these questions pushes human capability to its absolute limits. To study antihydrogen, scientists at places like CERN must create conditions more extreme than the void between galaxies. They must build magnetic bottles of incredible precision to hold atoms that annihilate on contact with any normal container. To do this, they engineer ultra-high vacuum systems, chambers so empty that the pressure inside is 1,000,000 times lower than the atmospheric pressure on Mars. They design and fabricate superconducting magnets that generate fields both powerful and exquisitely stable, fields that can gently cradle neutral antimatter atoms without touching them. They employ lasers cooled to fractions of a degree above absolute zero to slow the frantic motion of these atoms, making them still enough to measure. Each of these technologies represents a frontier of material science, cryogenics, and control systems. The mastery of such extreme environments does not stay locked in a physics lab. The techniques for creating and maintaining ultra-high vacuums are foundational for manufacturing the pure silicon wafers that become computer chips. The advances in superconducting magnets directly benefit magnetic resonance imaging machines, making them more powerful, efficient, and accessible. The precision laser cooling and trapping methods developed for antimatter are now tools for quantum computing and next-generation atomic clocks, which will redefine navigation and communication. This is the hidden engine of progress. Humanity's most ambitious questions force us to invent tools that reshape our world. We reach for the stars, and in doing so, we learn how to build a better microscope, a more sensitive sensor, a clearer image of the human heart. The quest to understand why we exist becomes the same journey that teaches us how to live longer, healthier, and more connected lives. It is a virtuous cycle where curiosity fuels invention, and invention, in turn, opens new windows back into the cosmos, allowing us to ask even deeper questions with even sharper tools. The search for our cosmic origins is not a solitary pursuit in a single laboratory. It is a vast, interconnected web of human curiosity, stretching across disciplines that once seemed worlds apart. To solve the asymmetry problem, we need the cosmologist's telescope, the particle physicist's collider, and even the condensed matter physicist's cryostat, all pointing toward the same hidden truth. Each field brings a unique language and a unique set of tools to the table, but they are all reading different chapters of the same cosmic story. Cosmologists provide the grand narrative. They look at the universe's large-scale structure, the faint glow of the cosmic microwave background, and the accelerating expansion driven by dark energy. Their models of the early universe's rapid inflation and its violent phase transitions set the stage. They tell us when and under what conditions the asymmetry had to emerge, defining the environmental pressures that any successful theory must withstand. They ask the big-picture questions, framing the mystery within the entire history of everything. Particle physicists, in turn, provide the alphabet. They search for the fundamental characters in this story, the particles and forces that act on the smallest scales. Their calculations predict decay rates and interaction strengths, while their massive experiments hunt for the fingerprints of new physics. They ask what specific actors could have performed the crucial act of bias, searching for deviations in the behavior of B mesons or the elusive signature of a proton decaying in a tank of pure water. They are the detectives examining the microscopic evidence left at the scene of the cosmic crime. Then there is the surprising contributor, the field of condensed matter physics. This discipline studies the collective behavior of billions upon billions of atoms in solids and liquids, phenomena like superconductivity and superfluidity. At first glance, this seems far removed from the first second of the universe. But here is the beautiful connection. Under extreme conditions, like near absolute zero temperatures, these vast collections of particles can give rise to emergent phenomena, where groups of electrons behave as if they were a single, new kind of particle, a quasi-particle. Some of these quasi-particles are theorized to be Majorana fermions, entities that are their own antiparticles, acting out on a tabletop scale the very same quantum properties that the neutrino might possess on a cosmic scale. By creating and manipulating these analogs in the lab, condensed matter physicists can test concepts of symmetry breaking and topological states that are devilishly difficult to probe in the high-energy realm of particle accelerators. They build toy universes in crystals of strange materials, offering a tangible, controllable window into physics that might otherwise be purely theoretical. This grand collaboration is more than just sharing data. It is a meeting of minds that speaks to the fundamental unity of science. The biggest questions refuse to be confined to a single department. They spill over, demanding that experts in the very large and the very small, in the hottest beginnings and the coldest laboratories, learn to speak each other's languages. A cosmologist's model of a phase transition informs a particle physicist's search for a new boson. A condensed matter experiment on a Majorana quasi-particle provides a crucial insight that reshapes a theorist's equation for leptogenesis. This breaking down of traditional barriers is not just efficient, it is essential. The operating manual of the universe does not come with separate booklets for stars, for atoms, and for solids. It is one integrated text written in a logic that transcends our human-made categories. The quest to understand why matter exists is weaving these disparate threads into a single, stronger cord, pulling us all closer to a revelation that will redefine not just a field of study, but our very conception of reality itself. The scale of this question demands a scale of effort to match. This is not a mystery any one nation, any single laboratory, or any solitary genius could hope to solve alone. It is a challenge that has forged one of humanity's greatest collective endeavors, a testament to what we can achieve when we channel our shared curiosity toward a single, profound goal. At the heart of this global enterprise is CERN, the European Organization for Nuclear Research, nestled on the border between Switzerland and France. But to call it a European project is to misunderstand its nature entirely. CERN is a global village. Within its complex of tunnels and laboratories, you will find over 10,000 scientists and engineers representing more than 100 countries from every continent on Earth. They are particle physicists, of course, but also computer scientists, cryogenic engineers, materials experts, and data analysts, a symphony of specialties all tuned to the same frequency. This is not a loose affiliation, it is a deeply integrated organism. A researcher from Japan might spend years working on a detector component built in Italy, which will be installed by a team from Brazil, to collect data that will be analyzed by a graduate student in India, all in pursuit of a signal predicted by a theorist in the United States. The language spoken here is not just English or French, but the universal dialect of mathematics, engineering, and the relentless pursuit of evidence. Consider the LHCb experiment, one of the 4 giant detectors positioned around the Large Hadron Collider's ring. While a TLAS and CMS made headlines by discovering the Higgs boson, LHCb has a more subtle, but no less critical, mission. Its name stands for Large Hadron Collider Beauty, and its entire design is dedicated to the forensic examination of beauty quarks and their antimatter counterparts. It is essentially a microscope built to study CP violation with unmatched precision. LHCb is not a machine owned by one institution. It is a collaboration of more than 1,400 scientists from 86 universities and laboratories across 18 countries. Every paper published, every new measurement of a particle's decay carries the names of hundreds of authors, a literal roll call of international partnership. This model of collaboration is not optional, it is essential. The technological and financial hurdles are simply too high for any one country to bear. The computing power needed to process the collisions from the LHC is distributed across a worldwide grid, a digital nervous system that shares the load from Seoul to Santiago. The intellectual challenge, too, benefits from a diversity of perspective, a novel way to analyze a tricky dataset, a clever workaround for a mechanical limitation, or a bold new theoretical interpretation can come from anywhere. This ecosystem thrives on a healthy tension. There is intense competition, certainly, a race to be the first to make a discovery or to achieve a more precise measurement. But this competition is carefully channeled. It happens within a framework of radical transparency and shared purpose. Data from the collisions are not hoarded by one team. They are the common property of the entire collaboration, scrutinized and debated in endless meetings and video conferences that span time zones. The goal is not to win for your university, but to win for the understanding. This transforms the endeavor from a contest into a conversation, a global dialogue with the universe. In a world often divided by borders and conflicts, places like CERN stand as powerful counterexamples. They are spaces where nationality, religion, and political belief are secondary to a shared identity as explorers. The fundamental laws of physics do not care about passports. The asymmetry between matter and antimatter is a puzzle for our species, not for a single nation. By working together on this monumental scale, we are doing more than just probing the secrets of quantum fields. We are practicing a form of unity, building a legacy of cooperation as enduring as the knowledge we seek. It is a reminder that the greatest mysteries of existence can and must bring us together. The path forward is illuminated not by answers, but by the sharp clarity of our remaining questions. For all our ingenious detectors and elegant theories, the core mystery of our material existence remains stubbornly unresolved. We have identified the crime scene, we have the list of necessary conditions, but we have yet to catch the primary suspect in the act. The central unknown is the exact source of the powerful charge parity violation required to seed the cosmos. The tiny effect seen in particle decays is a crucial proof of concept, a whisper that such a bias is possible, but it is billions of times too faint to build a universe. Where is the shout? Does it reside in the properties of the elusive neutrino? If these ghostly particles are indeed their own antiparticles, it would open the door to leptogenesis, a process where the decay of heavy neutrino cousins could have generated the initial imbalance. This makes the ongoing hunt for Neutrinoless double beta decay one of the most consequential experiments on Earth, a quiet search for a property that could rewrite cosmic history. Or does the answer demand something entirely new? The profound silence surrounding proton decay suggests that if Baryon number can be violated, it happens on timescales so vast they defy our current imagination, pushing the energy scale of new physics far beyond our present reach. This very silence, however, is a guide. It tells us that the particles or forces responsible for tipping the scales must be exceptionally heavy or interact in exceptionally subtle ways, forever hidden from the direct view of our current colliders. The staggering shortfall of the Standard Model is not a failure, it is our most important compass. The fact that its predicted asymmetry is 10 billion times too small is not a quiet discrepancy, it is a blaring alarm. It is the universe itself telling us, in no uncertain terms, that our map of reality is incomplete. Major pieces of the puzzle are missing, and their absence is written into the abundance of every galaxy. This recognition fuels a vibrant and dynamic frontier. The field is alive with competing ideas, from supersymmetry and grand unification to more exotic concepts involving extra dimensions or cosmological phase transitions. Each is a possible pathway, a different script for the first act of everything. The ongoing mystery ensures that the next groundbreaking discovery could come from any direction: a new particle in a future collider, a faint signal from a deep underground tank, or an unexpected pattern in the light from a neutron star collision. We are not at an end, but at a thrilling precipice. The unanswered questions are not a barrier, they are the engine of science, the very reason we keep building, keep searching, and keep looking deeper into the night sky and into the heart of matter itself. This delicate preference is the very signature of our reality. Our journey through the clues, from Sakharov's elegant conditions to the silent watches in deep underground laboratories, reveals a cosmos that was not born in perfect balance, but in a state of profound and necessary bias. We have mapped the territory of the unknown, identifying the precise gap between the faint whispers our theories allow and the thunderous abundance we see in the night sky. Each experiment, whether it listens for the decay of a proton or measures the fall of an anti-atom, is a sentence in a story we are still learning to read. The final chapters of this cosmic origin story, however, remain unwritten. The enduring enigma of why the universe favors matter transcends a technical puzzle in a physics journal. It is, at its heart, a quest to understand the precondition for our own existence. We are not passive observers of this mystery, We are its living consequence, made from the ashes of that first great annihilation. Every thought you have, every sensation you feel, is processed by a brain built from atoms that should not be here. That realization transforms the cosmos from a distant spectacle into a deeply personal narrative. As we look to the horizon, building more powerful colliders and more sensitive detectors, we are not just chasing abstract particles. We are edging closer to an answer that will tell us what the universe is truly made of, and by extension, what we are made of. The hunt continues in the quiet halls of global collaboration, where the shared goal of understanding bridges every border. What do you think the final answer will be? Does it lie in the ghostly neutrino, in a hidden symmetry, or in something we have not yet dared to imagine? Share your thoughts on this profound mystery in the comments below. If you want to join us for more deep dives into the great unknowns of space and time, be sure to subscribe. And the next time you look up at the stars, remember this: every single atom in your body, every element forged in a long dead star, is a survivor of the universe's first and greatest battle, a testament to a tiny, ancient crack in a perfect mirror.